Okay, everyone, welcome. Hopefully you can hear me. You hear me okay? Excellent. All right. Okay, before we get started, I want to mention that I'll have a quiz opening up on Moodle after the lecture today. This quiz will cover the material I've covered as of the end of this lecture. I might have to, depending on how far I get in this lecture, I may have to delete some questions that if I don't get as far as I plan on getting. In which case there'll be a little bit of a delay before the quiz opens. But the quiz will be on Moodle. It's on dropbox.csce.sc.edu. Not on Blackboard, it's on Dropbox. The quiz will be open for 1 week, so it'll automatically close next Wednesday just after class. You get 2 attempts to take it. The second attempt is the score. The score you receive on the second attempt is the score you'll have logged for the quiz. It's open book, open notes, open internet. So you'll notice that I try to make it challenging, even with all these resources available. So if it seems like it's tricky, it's I'm trying to make it as difficult as it should be, considering that you have all these materials in front of you. If you find any bugs or typos on the quiz, just send me an email. It's pretty common with these online quizzes. I format the quiz and then import questions, and it's fairly common for there to be some typos or bugs. So if you find any, just let me know and I'll fix it. And if I have to adjust anyone's score as a result of that, I have no problem doing that. Don't panic or freak out. It's not a big deal. The quiz currently has 10 questions, but like I said, I might have to drop a few depending on how far I get today. And again, that'll be on Moodle, which is dropbox.csc.sc.edu. If you have any questions logging in, let me know, or if you have any questions getting into the quiz. Okay, so last time I was talking about communication channels and protocols, and there's different types of those depending on the distance and the performance. Channels are like, when you say channels, it's kind of like the physical layer. And the questions on the quizzes are on this quiz will be multiple choice. So there's a variety of different types of communication channels and protocols. Channels are kind of like the physical layer, the electrical characteristics, and the protocol is kind of like the data link layer. If you're familiar with physical layer and data link layer, you might not have heard those terms. That's something you'll cover in CSCE 416 networking. But basically, the channel is the physical connection, and the protocol is the timing diagram that you have to understand for the operation of the channel. So there's channels inside chips, and that go from chip to chip, and of course there's networks. In this class, we're focusing on some chip to chip, and mostly we're focusing on the lower end, lower performance, lower power types of those. So I mentioned that when it comes to these channels and protocols, they can be asynchronous or synchronous. And I mention this because this is something that is emphasized in the 212 textbook, this idea of having a clock in the channel, which makes it synchronous, or not having a clock, in which case it's asynchronous. And so that's one way that you can categorize channels. It's not necessarily the end-all and be-all, but it's just something to be aware of. So in this class, we're going to talk about Uart, and I started on that last week. Uart is asynchronous. There's no clock in the channel. Of course, there is a clock involved. You have to have a clock when you transmit data, so you can synchronize the bits that you're transmitting, and you have to have a clock when you receive the data. So again, when to read the bits. But that clock is not present inside the channel itself. It's something that has to be prearranged and pre-agreed upon by both sides of the channel. Another option I mentioned last time, and this is a little bit outside the scope, but some channels don't have a clock, but the receiver is able to extract the clock from the channel based on the transitions, the bit transitions inside the channel. And in fact, that's very common these days. That's how PCI and SATA work. It's in other protocols, high-speed protocols typically work that way. Another option is a synchronous channel, which is where you have a clock. Clock is one of the wires inside the channel, and depending on the channel, the clock is usually driven by the side of the channel that is transmitting or initiating the transaction that's going on at the time. And so we'll be looking at SPI and I2C and JTAG, which are all synchronous. Okay, so I started this last time just to quickly review. UART stands for Universal Asynchronous Receiver Transmitter. Of course, asynchronous is right in the name of it, so you know it's asynchronous. UART is a very low performance protocol. It's been around for a long time, and it's still very heavily used for doing console access. So you know you can buy a very expensive piece of networking equipment or laboratory bench equipment, and oftentimes they'll still have a UART connection on the back, so you can plug in and get a quick and easy terminal. You know, you can get a command line, you can get a textual interface in there, which is, I think it's kind of funny actually that you know this really old protocol is still used on, you know, new high-end equipment. It's just kind of a universal way to get a terminal. Now you can send files through UART as well, but that's generally not what it's used for. It's not used for bulk data transfer. It's used for just basically keyboard and a terminal, keyboard and monitor, basically. So UART has 3 physical wires that make up the channel, and they're all single-ended, meaning that there's just 1 wire per bit. So 1 bit is conveyed on 1 wire, except for ground. Ground is just an electrical ground, and then you have transmit and receive wires. The thing that's kind of unique about UART as compared to the other protocols is that you have to connect the transmitter on one side to the receiver on the other, and vice versa. And that's important that you do that. And in that sense, UART treats both ends of the channel sort of equally. And in fact, the receiving and the two directions, receive and transmit, are completely independent from one another. So you know, and that makes sense, because if you're at a terminal, you know, you'll be typing stuff in, and then, you know, you hit enter, and then you wait for something to come back. There's not, they're not synchronized, and the transmit and receive are not synchronized in any way. And in fact, when we had the lab-based version of this class last spring, we did a project where we did just one of the wires. We just had one-way communication from the chip back to a terminal. And we didn't even bother to, you know, to implement the other side. So we just basically had 2 wires making up the channel. So it was unidirectional as compared to being bidirectional when you have both wires there. So UART normally has the channel when it's not being used, when no data is being sent, and this applies to both the receive and the transmit wire. The wire is at a high voltage at whatever VDD is. And so that's when it's idle. And then when you want to send a transmission, you put a start bit, you inject a start bit into the channel, which is when you pull the channel down, you make it ground, you ground the channel basically. But it's a start bit, and that means that the amount of time that you are holding the start bit, the amount of time that you're setting the channel to 0 to signify the start bit, is for one bit time, 1 bit slot, which is the baud rate, the inverse of the baud rate. So there's this notion of a kind of a time slot where the time is logically kind of discretized or split into slots, where the amount of time spent in each bit on the channel is the inverse of the baud rate. And so because it's an asynchronous channel, both the receiving and the transmitting side have to agree ahead of time what that baud rate is, that bit time or the bit rate of the channel. And that's kind of one of the things I don't like about UART. oftentimes boards will have a like you plug into an FPGA board or something, and a lot of times you kind of have to guess, and it's because the different UART channels use different speeds, but both sides have to have the same speed setting in order for the communication to. Okay, so you start out with the start bit, and then after your start bit, you send the data, which is usually 8 bits. It doesn't have to be, but it's usually 8 bits. Although one thing that is almost always the case is that the bits are sent from the least significant bit to the most significant bit. So that's the order of the bits. So this is a serial channel, so one bit is being sent at a time, and on the other side of the channel, the receiver has to then convert this serial stream of bits into a parallel, register or word or value or byte. And so the ordering of those bits is important for that. So when the receiver receives the bits, it has to essentially fill them into a register from right to left. Okay, so that's pretty typical in UART. It's not the case in the other protocols we're going to talk about, but in UART, it's like I said, it's usually least significant bit to most significant bit. After the 8 bits are sent, or however many bits comprise a word, then there is either a parity bit, which is optional, or a stop bit. Stop bit is when you just pull the channel high for 1 bit time, and that signifies that the transmitter is done. Now, why is the stop bit 1? So remember, the start bit is 0. So the channel is normally high. That's the idle state. And then the stop bit is also high. The start bit is 0. So the channel is normally high. When you want to start, you pull it down. Whoever's sending is going to pull it down. When I say pull it down, I mean set it to 0 or short it to ground through a transistor. And then when you're done, you let it go. And so the idea is that why is the stop bit 1? It's because if you were to send another byte, another transaction immediately following this transaction, you want to make sure that there's a distinction made, that you have a stop bit which goes high, and then later the next one you'll pull the start bit down. If you try to do consecutive transfers without the stop bit, you would end up with a framing error. You'd get it's this notion of a framing error. You would try to push 2 transactions too close together. The stop bit basically allows you to go back to kind of the idle state of the channel before you then pull down the start bit again to signify a new transaction starting. And so I mentioned that there's a parity bit. This is something that's optional. So if there is a parity bit, that's something along with the speed of the channel, the baud rate. That's something that both sides of the channel need to agree on a priori before they start using the channel. The parity bit is an error detection bit. It allows you to detect if there's an error, if there's up to 1 bit error. But it also, if you know there's an error, if somehow you know that there's a bad bit in the transmission, then you can use the parity bit to actually fix that. So that's the distinction between whether you know there's an error or whether you don't. If you get a transmission and the parity bit is not what you expect it to be, then you know there's an error. If you get a transmission and you know a specific bit is wrong, you can use the parity bit to fix it. So there's odd parity and even parity. This part is a little bit more confusing than you might expect it to be. So the way the parity bit works is that the data bits and the parity bit are looked at together. And if you have odd parity, if the channel is marked as having an odd parity bit, then when you look at the data bits and the parity bit together as a collection of bits, the number of 1 bits in there should be an odd number. So what that means is that as the transmitter, I have to set the odd parity bit to 1 if the number of bits in the channel was even, because I have to, what I'm basically doing is forcing the number of bits between the channel and the parity to be odd. So basically, you look at the number of bits in the data. If it's even, you set the odd parity to 1, which sounds counterintuitive. It's like, wait a second, like, why would you set odd parity to 1 if the number of bits is even? That seems counterintuitive, but it's not. It's just the idea is that you look at the combined number of bits and the combined bits in the data and the parity bit, and there should be an odd number. And then likewise, if the channel has been marked as having even parity, then the same thing applies, except the parity bit would be used to force the number of 1 bits to be even between both the data and the parity. So I'll show some examples of that. That's a little, I think that's a little counterintuitive, and you can kind of get wrapped up in that a little bit. The baud rate is as I mentioned earlier, the baud rate is the rate at which the bits are sent across the channel. This is a little confusing because the baud rate basically just determines what 1 bit time is, how much time you allocate for each bit in the channel, and so it's measured in bits per second. So you might think, well, that's the amount of how much data I push to the channel. But there's a subtle distinction. The baud rate is including, it's the bit rate, but it's including the overheads of the start bit, the stop bit, and the parity. So if you look at the actual throughput of the channel, the usable throughput from the application perspective, like if I'm pushing data through the channel, the throughput of the channel is actually the baud rate, but you have to multiply by the ratio of data bits divided by the total number of bits per transaction. So it would be the number of data bits divided by the number of data start, parity, and stop bits. Keep that in mind. The throughput, the effective throughput is less than the baud rate because of these extra control bits. Okay, so here's an example. Now in this case, this example here, it's a timing diagram. You may not be used to reading these timing diagrams. I'm hoping that in this class you'll become comfortable with these fairly early on, because we'll be looking at a lot of these. This is supposed to kind of look like it's a graph where the horizontal axis is time and the vertical axis is basically just 1 or 0, or sometimes you may have multiple bits in there. But for now, we're just looking at 1 or 0, so high or low. So this is meant to kind of look like an oscilloscope, kind of. Now you'll notice that when you have a transition, as you read the timing diagram from left to right, you'll have transitions from 0 to 1 or 1 to 0, and those transitions are not instantaneous. Their slope is not infinite. Their slope is high. It's kind of like it kind of slopes upward, and that's meant to represent the rise time, how much time it takes to to charge up or to discharge the wire. But it's just kind of it's not really meant to represent how fast you actually are able to do that. It's not like you can look at the slope of that line and measure the capacitance of the channel. It's just kind of a stylistic thing. The little slopey lines as they go from 1 to 0 or 0 to 1. Now, if you have an area there with kind of a gray area, that's meant to represent a don't care. So we don't really care what the value is during that time. Although in this case, I just realized that technically the don't cares at the beginning on the left side are a little bit, they actually shouldn't be don't cares, because I mentioned that it's important that when the channel is idle, the receive and the transmit wire should be high. So it's actually, I'm going to need to fix that. It shouldn't actually be a don't care at the beginning. It's important to understand that the channel is normally high when it's idle, and then the first thing that happens when you send a transmission is that you drop it down to 0, and that's the start bit. Now you'll notice on the timing diagram there's also some dotted lines that are on there for convenience, and those are marked off every bit time. Basically think of it as a clock cycle, but in the channel this is the amount of time that's spent for each bit. How much time is spent per bit? Well, that depends on the baud rate. We don't really care what the baud rate is, so there's no kind of like, there's no actual numbers there on the horizontal axis. The only thing we care about is what's happening within each bit time. The actual physical bit time, length of the bit time, depends on the baud rate. So in this case, we have 7 data bits. We're sending the least significant bit first. There's no parity in this case, and there's 2 stop bits. which is kind of strange. Now, technically, you can have 2 stop bits. That's a possibility. It's not real common, but it's possible. So so what you're expecting to see here is if there's 7 data bits, no parity, and 2 stop bits, and of course there's always 1 start bit. So that would be 7 data bits, 1 start bit, and 1 start bit and 2 stop bits. So that would be 10 total bits. So the data throughput on this channel would be 7 data bits divided by 10 total bits, and then multiplied by the baud rate would be the effective, how much data we can actually push through the channel if we, take out the effects of these 3 additional bits, protocol bits. So you've got a start bit there, and then if you want to read the values, you just kind of work your way from left to right. And I don't know if you can see my mouse cursor if I'm in presentation mode, so I'm going to back it off of presentation mode here. So you start out here, this is the start bit, and then I'm going to read from left to right. So I'm transmitting a 0, 0, 0, 0, 0, 0, and then a 1, and then the last 2, of course, are the stop bits. So there should be 1, 2, 3, 4, 5, 6, 7 data bits. They're kind of sitting in the middle there after the first bit and before the last 2 bits. And those are the data bits. And it's least significant bit first. So when I read this as a value, I'm going to have to read it basically from the right to the left if I'm reassembling this as a value. So if I go over to the right-hand side, I've got 2 stop bits. So I'm going to walk in 2 bit slots from the right. I'm going to start here. So my first bit is going to be a 1, and then I'm going to have 6 zeros. So that's 1, 2, 3, 4, 5, 6. Let me actually hold on a second. I have a yeah, sorry, I have this have it annotated here. Yeah, so here's the start bit. As I mentioned, there's 2 stop bits. And then as I'm reading now from right to left, and I'm going to start not all the way to the right, but to the 3rd bit from the right, because I have to ignore that the last 2 bits are stop bits. So that's going to be a 1, 0, 0, 0, 0, 0, 0. So 1 and 6 zeros, which in hexadecimal notation, that should be, well, actually, that should be a 4 and a 0, right? So that's, let me update. Should be 4 and a 0 because it's 1, 0, 0, right? In binary, that's 4. And then 0, 0, 0, 0, that would be a 0. So if we convert this to hex, it would be 4, 0. And again, that's just reading basically from right to left. And you have to make sure you skip the stop bit to do that. And then likewise for the other side of the channel, what I'm receiving. So this is from the perspective of someone on the channel. I'm sending a 4, 0 in hex in 7 bits. And again, I've had to agree with the other side that the data is 7 bits. So 7 bits, 7 data bits, 2 stop bits, no parity bit. And so in this case, I'm reading again from right to left is 0, 0, 1, 1, 1, 1, 1, which would be a 1F if I reverse those bits and then I group them by 4s from the right to the left, and then convert each 4-bit chunk to a hex digit, as hopefully you guys are comfortable with from 211 and 212. Now 7 bits is not a multiple of 4, so even though I have 2 hex digits here, that's not to imply there's 8 bits. It just means that when I take 7 bits and convert it to hex, the values would be from 0 to 7F. You can't go above 7F with only 7 bits. You can't get from 80 up to FF. So that's how you decode that. You just, like I said, you're looking at the timing diagram and picking out the bits there. You just have to make sure that you're looking in the correct slots there. I also mentioned last lecture, I want to repeat it here. This timing diagram is also a little misleading too, because it sort of implies that the transmit and the receive are operating together, that they're synchronized, and they don't need to be, as I mentioned, not with Uart. Now they do with SPI, but I'll talk about that when I get to SPI. It's another protocol. Okay, so here's an example. This is something that I would ask. This is actually, this came from the exam last semester. This is similar to a question I'll ask on the quiz. In the following Uart transaction, what bytes are exchanged? So the reason I say exchange is because there's a transmit and a receive going on at the same time. So this is 9 data bits now, least significant bit first. So again, I'd have to read from right to left. And like I said, I think all the UART questions will be LSB first. Even parity now and 1 stop bit. So there's 1 parity and 1 stop, and the parity and stop are on the right-hand side. So again, I'm going to start from the right, but I'm going to walk into the 3rd bit from the right. I'm going to start there, and that's going to give me I'm going to skip the first 2 ones because those are the parity and start. So it's a 0, and then another 0, and then a 1, 1, and then a 0, and then a 1, 1, and then a 0, 1. And I'll stop before I get to the first bit because that's the start. So hopefully that adds up to 9 bits, and it does. So when I group from right to left, it's 1101 is the first group of 4. That's a D in hex. And then I've got 1001, that's a 6, and then a 0. So 06D, 06D. I'm going to show the answer here in a second. And then in the one below, I've got a missing bit. I have a bit slot here which I don't know what it is, but I should be able to figure it out from the parity. So in this one down here, if I look at count the number of 1 bits, there should be an even number, and that's for the data and the parity. So in order to do this parity calculation, I have to skip the start bit, and then I have to start with the least significant data bit here first. Is the leftmost data bit. So I have if I count the number of 1 bits, there's 1, 2, 3, 4, 5, right? And then there's a 1 bit at the end, but that's the stop bit. So I have 5 that I can count, but there shouldn't be 5. There shouldn't be if the parity is even, there should be an even number of 1 bits. So what that means is that one that's missing must be a 1. That must be a 1. That should have been a 1, because that would give me then 6 1 bits between the data and the parity, which is an even number, and that would match up to the fact that I have even parity. So the answer to that one, the missing slot there, should be a 1. Okay, so I've got everything annotated here. So there's the start bit. So there's the 6D. Actually, it should be 06D technically, because there's 9 bits. So I'm going to add another hex digit to pick up that 9th bit. So yeah, I'll say 06D is the data that's being transmitted, and then going the opposite direction, it should be EE after I fill in that bit. So if I go to the bottom transaction, that's a stop bit, and skip the parity bit, and then I've got 0. The first bit is 0, so that's the leading 0 that I added there in hex, and then I should have EE, which is 1110, right? So 1110, 1110. Yep, it works out. And as I mentioned, the parity bit is 0, so there should be an even number of 1 bits, including that one that's missing. So that's how you read that. Is there any questions about that? Okay. Okay, here's another example question. Assume you have a UART channel that operates at a baud rate of 9600 bits per second, and it has 7 data bits, 1 parity bit, and 1 stop bit. And I didn't say how many start bits it has, but the start bits is generally 1. So what's its throughput? That basically means I'm sending 7 data bits, but I need to also add in, when I do a transmission, it has to include the parity bit and the stop bit and the start bit, so that would be 10 in altogether, right? So 7 plus the 3 other guys, so that would be basically I'm getting 70% of the channel. So I would take 70% and multiply it by 9600, and that's 6,720 bits per second, right? So just 70.7 times 9600. Okay, so here's another missing bit question. So this is odd parity now. So, and there's 2 stop bits. So this one's a little bit convoluted. So starting from the right, I've got 2 stop bits. I'm going to skip those. Then there's a parity bit. So including the parity bit and working my way up through the data, not including the start bit, I'm going to count the number of 1 bits I have. So that would be 1, 1, 1 there. So 3 1 bits, right? There's 3. And there's odd parity. So I already have an odd number of 1 bits, even without including that blank space. So that blank space must be 0, right, to correct that error. So yeah, 0. Okay, so how about this one? Are there errors in the transaction below? So if I get this transaction, I've got an odd parity, but I don't necessarily know of any of these bits being wrong, but I can check the integrity of the channel by parity calculation. So if I'll skip the stop bit at the end, and I've got 5 data bits, so I'm going to count the number of 1 bits here. So on the transmit side, I've got basically just 1, right? And so 1 is an odd number, so the transmit side looks good. The receive side, I've got skip the stop bit. I've got 1, 2, 3, 4. I've got 4 1 bits in the data and in the parity, which is an even number, but I'm supposed to have odd parity. So obviously there was an error. The receive side had an error. I don't know which bit was an error, but I know one of them, at least one of them, is wrong. So I need to signal an error there. Something happened. There was a signal integrity problem. So the received parity is incorrect. Okay, so that's really all there is to UART. It's pretty simple. There's not much to it, and the reason for that is that it's a very low speed protocol, and so the reason why it's so simple is because the reason why it can be so simple is because it's so low speed. You can have 2 ends of the transmission that have their own clocks, and you don't and the problem, of course, as you might imagine, is that your clock frequency that you're using to send and receive the data is the same, but there's no guarantee the phase of those clocks will be the same. So it's a little dicey, but when you're operating at such low speed, that's okay. And also, frankly, you usually don't really care much if there's if there's a screwed up character because you're doing a console. It's usually not catastrophic if you have a screwed up character. Okay, so I'm getting pings. Yes, on the even parity example, why did you skip 2 bits from the right? Yes, even. That was this one, right? Okay, even parity. So this one had how many stop bits? Oh, it says in here 1 stop bit, right? So I actually didn't mean to do that. Actually, if I said that, I said that incorrectly. I'm sorry. Thank you for clarifying that. So with the even parity example, there was 1 stop bit. So if I'm counting the number of 1 bits for the parity calculation, I would only skip the first bit on the right-hand side, the stop bit. However, if I'm trying to look at the data that was sent, then I would skip 2 bits because the parity is not part of the data, but it is part of the parity calculation, right? So that part is a little kind of subtle, right? If you're looking at the data being sent across the channel, you're only looking at the data bits. But when you're doing the parity calculation, you have to look at both the data bits and the parity bits together when you're counting the number of 1 bits. Okay, so that part's, I think it's a little confusing. Okay, so just keep that in mind. Okay, so what about SPI? This is another very common chip-to-chip channel technology. SPI stands for Serial Peripheral Interface. So SPI, unlike UART, is synchronous, which is good because you don't need to use trial and error to figure out what the channel speed is when you plug a terminal into a device. I mean, again, assuming that you don't want to look it up. Just to be clear though, like when you get an FPGA board or an Arduino board, It generally doesn't come with any documentation. You know, you get a box with a board in it, you plug in. It's really usually, you know, it's difficult to look that stuff up. So often it just comes down to kind of guessing what the UART settings are, at least in my experience. But with SPI, you know, you don't have to worry about guessing the speed or setting the two sides of the channel to have the same baud rate or speed, because it's synchronous. There's a clock that's in there, and that also allows you to you know, you can, if you've got two chips that are closer together, you know, you can run it a little faster. You know, you can speed up the clock. You know, in fact, you could run it as fast as you want, and as long as the physical channel can support the clock rate that you're trying to put into it. Unfortunately, with SPI, and you know, I think they kind of blew it with SPI because it turns out that even though you don't have to set the speed of the channel or the number of parity bits, you still have other settings that you have to have both sides of the channel agree on before you start using it. And not only that, but those settings are much more subtle than the UART settings. And you'll see what I mean by that in just a minute. So you still have to, whenever you connect two devices with SPI, you have to make sure they're set up the same way, basically. SPI also assigns each device a role. So each device that's connected to an SPI on an SPI channel has to be designated as a specific role, and as a result of that, you don't have to switch the transmit and the receive wires like you do with UART. So the wires are connected. Each wire has a name, and you connect that wire to the same names on all the chips on the channel. So that's a nice thing. But the drawback of that is that only one of the devices on the channel can initiate a transaction. So you have masters and you have slaves, and each channel can only have one master. You can have multiple slaves, but only one master, which means that basically every SPI channel, you can only have you know, one device that can initiate an action on the channel, unlike UART, where you know, you plug a UART thing in and either side could talk whenever they want to. So that's kind of bad. Now the other thing is that all the transactions on an SPI channel are synchronized and bidirectional, meaning that anytime there's a transaction on the channel, you send data in both directions, and you send an equal amount of data in both directions, which sounds good, except it's hardly ever used because most applications don't require that. And I'll talk more about that. So that's kind of the drawbacks of SPI. Okay, so as I mentioned, there's a SPI has a master that is the entity that is initiating transactions. So the master role is the only one that can you know, initiate something on the channel. You can't have more than multiple slaves. When the master initiates a transaction, the slave that the master is talking to has to follow through and complete the transaction, essentially. SPI is byte oriented, and if you downloaded your own copy of the slides, I actually updated this bullet to be a little bit more precise. So SPI is generally operates in units of bytes, but you can send more than one byte when you do an SPI operation. But basically, the transmissions are multiples of 8 bits. The bit ordering, however, is application defined. So as I mentioned with UART, you always go least significant to most significant. With SPI, it's really up to it's more of the bit ordering as a setting on the channel. But obviously, all participants must agree on that. If you do okay, so I'll talk about that last bullet here in a little bit more detail in a minute here. Basically, the way SPI is set up is that the master is the one that drives the clock. So I mentioned SPI is synchronous, meaning that there's a clock inside the channel. Who is determining the clock speed and who is setting that clock? That's the master. Generally, it's a few megahertz, but you can drive up an SPI channel, pretty fast. I think up, in theory, you could go 100 megahertz, but usually they're more like 10. in that area. So basically the master has this, in addition to the clock, it has this signal called SS, slave select. And the slave select is what initiates a transfer. So normally the slave select is high. Just kind of like, remember in the Uart channel, like when the channel is idle, it's just high. It's high as in it's the VDD voltage, it's the supply voltage. So the SS is normally high, and when you want to use the SS, you drive it low. So that means it's active low, or it's basically it's negative logic. And so the master starts up the channel by driving SS to 0. And then during each cycle, during which time the channel is active, you send bits out one at a time. So again, this is a bit serial protocol. And so the master sends out a bit to the slave, just like with UART. But the difference is that the slave is expected to send one back every cycle. So the operation, the slaves or the master sends a bit and the slave sends a bit backwards, and they're happening simultaneously. So they're operating in lockstep. So what this is kind of a basically is an exchange. I call it an exchange. Every time you send a byte, you get back a byte. And the way that they're generally shown is kind of like a shift register, where the master is shifting one bit at a time into the slave, and then the slave is shifting one bit at a time in the master. And after 8 clock cycles, you will have effectively shifted a 16-bit value by 8 bits. And because that 16-bit value is kind of spread across the master and the slave, it results in this exchange. So talking a little bit more specifically about the signals. So remember that UART was 3 signals nominally. It was a transmit, a receive, and a ground. Although I mentioned you could actually do it with 2 channels if you're fine with unidirectional traffic. But SPI, on the other hand, requires 4 signals. So there's the clock, as I mentioned, and there's the slave select. And those are both driven by the master. And then there's 2 signals called MOSI and MISO. And MOSI just stands for master out, slave in, and MISO stands for master in, slave out. So obviously the master is setting MISO and the slave is setting, the master is setting MOSI and the slave is setting MISO. So the slave only gets to drive 1 signal, and the master gets to drive the other 3. And so I mentioned that the slave select is normally high when nothing's going on the channel, and it's low when you're engaging the channel and performing a channel operation. And also, the clock is also idle outside of an active transmission. So if you're not doing something on the channel, the slave select is high, and the clock is dead. It's just a flat line. Now you might say, well, is it flatline high or is it flatline low? Well, that depends on one of the settings called clock polarity. So the polarity of the slave select is always the same. It's always active low, but the clock may spend its time high or low outside of a transmission depending on that setting. So let's talk about those settings now. So there's CPOL and CFA. CPOL is the clock polarity. And so if the clock polarity is 0, that means that the clock spends its idle time at 0. And if the clock polarity is 1, it means the clock spends its idle time at 1. When I say idle time, I mean outside of an active transmission. CFA stands for clock phase, and this one is the one that's a little bit trickier. So the clock polarity defines when the data change. The clock phase rather defines when the data changes relative to the clock. So when the CFA is 0, it means that the data actually leads the clock a little bit. So during a transaction, the data changes a half cycle before the clock changes. So basically, when CFA is 0, it means the data gets a head start. And when CFA is 1, it means the data doesn't change until the clock changes. So the first edge of the data also corresponds to the first edge of the clock. So basically, the difference here is a 1/2 clock cycle, where when CFA is 1, the data gets a half clock cycle head start on the clock. Whereas if CFA is 1, the data and the clock change at the same time. In other words, saying that again, just make sure I didn't screw that up. When CFA is 0, the data wires get a half clock cycle head start on the clock. When CFA is 1, the clock and the data start at the same time. So between the C pool and the CFA, those two settings together determine the SPI. Sometimes people call it the mode. So there's 4 modes because there's 4 different ways that you can set those two settings between 0 and 1. Now, oftentimes, like in the when you use SPI on the Atmel chip, you also define the bit ordering as well. It's the 3rd setting. I mentioned that you could go least significant bit first or the most significant bit first. In other words, you can send the data through forwards or backwards through the channel when you serialize it. So that's kind of a 3rd setting. But when people say SPI mode, they're usually talking about these 2 settings in particular. So for example, you might have, here's an example where you have C pool is 0 and CFA is 0. Now, by the way, I'm telling you what C pool and CFA are here. It's stated, but you don't need me to tell you that, because you can tell both of those things just by looking at the timing diagram. The clock, if I look at what the clock is at the very beginning, when the clock sort of, before it really starts pulsing here, before the transaction starts, the clock's 0. So I know that the C pool is 0 just by looking at what this clock is doing before the transaction starts. And with CFA, all I got to do there is look at when the data changes. So the data starts out, MISO and MOSI are the data. I don't care what they are before the transaction, so that's why they're shown as don't cares. But I can see that they go to being not don't cares. In other words, their first edge, when they become valid, is a half clock cycle before the first clock edge. So this is the head start I was talking about. Notice how these guys change from don't care to care before the clock ever gets to do anything. It's still 0. The clock doesn't even jump into action until a half clock cycle after the data starts. So that's why CFA is 0. Now you might say, well, wait a second, what happens if I get these wrong? What happens if one side has a mode of 1, 1 and the other side has a mode of 0, 0? The data will be corrupted. You won't get, the timing will be off, basically. So you won't get the right data. It'll be broken. Now it may not be catastrophically broken. You may only be off by 1 bit, but it's for all practical purposes, your channel is messed up, is inoperable. So you got to make sure that these C pool and CFA are the same on both sides of the channel. Okay, so this slide shows, and by the way, just to be, the reason I'm using this view is because I want to make sure you can see my mouse cursor. So this shows all 4 possibilities. So this is the same transaction. Oh no, it's not the same transaction. Actually, they're different. Yeah, I guess, okay, so it's not the same data, but we've got all 4 modes. So as I mentioned, when C pool and CFA are 0, clock starts out as 0, and then the data gets a head start on the clock by 1 half cycle. Now, if I change the CFA to 1, and so I'm going to move over to the top right hand timing diagram, you'll notice that the clock, the first edge of the clock, and the first bit that's changed on the data, both MISO and MOSI, because they're operating in lockstep. MISO and MOSI are synced up perfectly. Those guys are changing. The first time they change is also the first time the clock changes. So you notice that the clock rising edge corresponds to the rising edge of both the MISO and MOSI, just because the first bit I send is 1. So of course the first edge is going to be a rising. Okay, so what that means is that when the receiver senses the data, you want to make sure that you read the data on the opposite edge of the clock that it's changing. So in the case of over here, when CFA is 1, the receiver is going to be reading the data on the rising edge of the clock, right? Because at the first rising edge of the clock, the data is already stabilized because it changed a half cycle earlier. But when CFA is 1, I don't want to do that because the clock is changing with the data. I don't want to read the data on the rising edge of the clock because the data is in flux at that point. So I would want to read the data on the falling edge of the clock, which is why it's referred to as the phase. So the clock phase is different. So if I have C pole is 0 and C fuzz is 1, I'm reading the data on the falling edge. And if it's 0, 0, I'm reading on the rising edge. Well, that seems pretty simple, right? Well, the problem is that when you change C pole, then you have to change those things as well. So when C pole is 1, again, the data is ready to be read on the first edge. Well, the first edge of the clock is going to be falling because the clock is normally 1 because of the C pole being 1. So when you have C pole 1 and C fuzz 0, I'm reading on the falling edge. So because I changed the C pole, even though I kept C fuzz 1, I have to switch clock edges. Likewise, when C pole is 1 and C fuzz 1, I'm now on the rising edge of the clock when I read my data, because the data will, of course, be changing on the falling edge because it changes with the first edge of the clock, which is going to be falling because the clock starts out as 1. So these are the 4 different operating modes of SPI. And really, the C pole and the C fuzz is really just about which edge you want to read the data on, basically, is really what it comes down to. And then notice that I also have on the top, I'm reading the most significant bit, or I'm transmitting the most significant bit first, and on the bottom is the least significant bit first. But in this case, because I'm not reading the bits in this case right now, I don't really care. But that is a setting, just to be aware that that's a setting that both sides of the channel have to agree on, or obviously it's not going to work. So this, it's kind of, these are basically dialects of the protocol that have to be agreed on a priori. Okay, so here's an example question. In the following SPI exchange, what is the value sent from the slave to the master? So when I say from the slave to the master, what I'm really saying is that you're supposed to be reading MISO. Why MISO is master in, slave out. So this is the return connection. This is the MISO is what I'm getting back. Okay, so what is it? Well, in this case, you don't have a start bit and you don't have a stop bit. And there's no parity bit. So that makes things really easy, actually, in terms of reading the data, because the only thing that you're sending is data. So all you got to do is just read everything. You don't have to worry about skipping the last bit and skipping the first bit and skipping the parity bit if there is one. So it's much easier to read the timing diagram. So in this case, the data is, I can just tell from looking at, I don't even have to look at what C pole and C fuzz is. I can tell that if I'm reading this data, I best be reading it on the rising edge of the clock, just because I know that on the falling edge, the data is changing. And again, I'm judging that just by looking at, the timing diagram. So I'm going to use the rising edge of the clock, and it just so happens that my dotted lines here happen to line up on the rising edge of the clock. So I just have to look at the dotted lines and count from there. So basically, MISO is a 1, right? So I'm basically looking where the dotted line intersects the signal. So it's a 1 0 1 1 0 1 0 1. I can read this one much faster than Uart because it's actually easier to read the data. Now it's the most significant bit first, so I can read this from left to right. And as I mentioned, SPI is multiples of 8 bits, so now I don't have to worry about, oh, what if it's 7 bits? What if it's 9 bits? This is a multiple of 8, and it's most significant bit first. So this is great. This is a 1011, which is 11, which is B in hex, right? And then 0101, which is 5 in hex. So these are super easy to read in this case. And so here I've annotated this diagram to make it clear what's going on. So I've circled MISO because I asked from slave to master instead of master to slave. Of course, I could ask you for both, in which case you'd have to read, both bytes. But in this case, it's MISO, and then I've put the little lines here where I've drawn where the data is changing. So now this is a little confusing because the lines I've drawn in red are meant to indicate where each bit starts and ends. But the dotted lines that are already in the timing diagram happen to be lined up on the middle of each of the bit times. So when I was reading this, I was actually looking at the dotted lines here and where they intersect each of the signal lines. But when I draw these other lines here, I can actually, instead of looking at I can look at the whole, interval. So you can see that's high, low, high, high, low, high, low, high. And then I convert that to hex here, which is B5. So that's pretty, I think that one's a little easier to read than Uart. Uart is stressful. Too many options and extra bits. So here, example, in the following SPI exchange, what is the value sent from the master to the slave? In this case, I'm looking at MOSI because it's master to slave. And now you're given CPOL and CFA, but I don't care because I'm just going to look at what edge of the clock I should be reading. Now, in this case, I can see that the data is changing on the falling edge of the clock, unlike the last example. So I'm going to read the data on the rising edge of the clock because that'll each rising edge of the clock is smack dab middle of the bit. Now, unfortunately, the dotted lines in the timing diagram are not lined up with that anymore. Now they're lined up to where the data is changing, which is fine. I'll just look at what the bits are between the dotted lines instead of on the dotted line. So it's basically, now it's most significant bit first again, so I'll read from left to right. So it's 1010, which is 10, which is A in hex, and then 0011, which is 3. So A3, and that's my byte, and that's, I kind of showed where these, it didn't line up. Yeah, that's better. Line these up a little better. There we go. But yeah, there's the data, and then I marked off the bits. And you know, again, in case you're a little confused by this, the bits are, you know, you're looking at the level here of the signal. So if the signal is high, it's a 1. If it's low, it's a 0. It's a little hard to read sometimes though because you've got multiple signals stacked on top of one another. So you have to kind of think about, you know, sort of what the baseline is for each signal. So in this case, MOSI, there's a kind of a hidden, there's a baseline here that would run vertically across the bottom here, which would match up to where the ground is. But you don't see a baseline, so you have to think, well, you just have to distinguish between high and low. Okay, so here's where things get a little crazy though with SPI. So when you read single, I want to make sure I get the word right, transactions. Sorry, I screwed it up. I knew I would. When you read single exchanges, sorry, let me back up here. This is an exchange. I always screw up this terminology. I knew I would. An exchange. An exchange is the master sends a byte, the slave sends a byte. They're done simultaneously. That is an exchange, right? Now, I mentioned earlier that nobody really cares about doing exchanges in real life, except maybe if you're doing, I don't know, like audio. There's some applications, but in general, no one does exchanges because what people really want to do, what applications demand, is a programmed I/O, which is what I described in the last lecture. Programmed I/O is where I can do a read operation or a write operation. So either I have a peripheral, I want to read a control register, or I want to read a status register or write a control register, which, as I mentioned, those terms are out of date. So I'll just say, you know, I/O register. I want to read something on the peripheral. I want to write something on the peripheral. I don't want to do an exchange. Who cares about doing an exchange? That's dumb. So basically, an SPI exchange is one of these exchanges, but an SPI transaction is when I superimpose a programmed I/O operation on top of SPI, which requires multiple exchanges, in which case some of the bits that are sent during the exchanges are don't cares. So what I mean by that is basically, well, first of all, let me back up here and speak more generally. So an exchange is one byte exchange, whereas a transaction is when I do multiple bytes kind of back to back. Now, I mentioned back when I first started talking about SPI that there's a slave select signal that signifies when the bus is active, when there's an active transfer, okay? Now, the master, the transfers are all in units of 8 bits, but you don't have to stop transferring after 8 bits. You can do multiple exchanges of 8 bits while holding the slave select low, right? In other words, I don't have to just limit my transactions to 8 bits. I can do 16 bits or 24 bits or 32 bits or 48 bits, right? Whatever, right? Or 40 bits, right? I can do multiples of 8 bits exchanges, which together signify a transaction. So basically what I'm saying is that as long as the slave select is low, I could do multiple exchanges, and those together form a transaction. And so the transaction can be multiple exchanges, right? Now you might say, why are you emphasizing that? Who cares? Well, remember, with Uart, that was not the case. I could not do back-to-back Uart transactions because after I sent the data and the optional parity, I had to do a stop bit. I had to stop. I had to send one Uart transaction at a time, and I couldn't chain them together. That's not allowed. If you do that, you get a framing error. But with SPI, on the other hand, I can hold the slave select low, or the master can hold it low, and you can do multiple 8-bit exchanges. You could do the master could do as many as it wants. In fact, it can monopolize the bus. It can just always keep slave select low if it wants to. Okay, so that's one of the distinctions between Uart and SPI. That's, I think, a little. It can be confusing, of course, when you're learning Uart and SPI at the same time, and you might get that confused. So again, Uart, you cannot chain transactions with Uart, or chain exchanges, I should say, or transmissions, right? Because Uart is one way you can send one word, but you have to stop each word before you start the next word. Whereas SPI, you can chain them together. Okay, so why am I talking about this? Well, this leads into this discussion of superimposing a programmed I/O. So what you can do is you can implement another protocol on top of SPI. So SPI just defines what an exchange is, but I can then, as an application designer, say, well, I want to be able to implement multiple SPI exchanges, and those will form a transaction, and the transaction can then be a programmed I/O read or write. Okay, so the way that works is that if the master wants to read an address, a register from the slave, then it will do 2 exchanges, 2 byte exchanges. The first byte will allow the master to send the address of the register it wants to read, along with flags, where the flags can be like, well, whether you're doing a read or write, or if you want to do a streaming, a multiple read or write, right? Multiple consecutive reads or writes. And those are in the flags. Now, the address and the flags have to fit within 8 bits, or generally, well, at least in our experience. I suppose you could probably have an exchange protocol. A transaction protocol. Sorry, I always screw up those 2 terms. You could implement a transaction where you could have a 2 exchange or a 2 byte header, basically. But in our experience, we've never seen one that did that. Generally speaking, the first exchange has all of the header information, basically the flags and the address, right? And then the second exchange, the second byte, is the data, and then if you can also have additional bytes after the second one that have further data, right? So basically, you end up with a sort of a packet, sort of, when you think about it, where the first word is the control information, and the subsequent words carry the payload, the data. But here's the thing that's crazy about this. When you do this, the master in the first byte sends its stuff over to the slave, tells it what it wants to do, read or write, the address, but the slave has to send a byte back, right? But what's it going to send? It has nothing to send because it doesn't know how to respond to the master until the first exchange has completed, right? So basically, the slave sends back dummy data, don't cares, right? Just kind of wasted bits. Now, it probably, and I don't know if I ever looked at this actually, but I would imagine in practice it probably just holds the master in, slave out, MISO. It would just hold that, hold it 0 or 1, whatever. But it doesn't send any data. Then in the second byte, if the master was doing a read, then in the second byte of the transaction, the second exchange, the master would then send dummy data to the slave, and then the slave would send its response back, whatever data was being read that the master was requesting. So the master would say, in the first exchange, it would say, I want to read address 10. And then during which time the slave sends nothing back. And then in the second exchange, the master sends nothing, and the slave sends its response, right? So this way you get a protocol where the master makes a request and the slave responds, and this all happens within one transaction. And again, I'm defining a transaction as the time when the slave select is held low, and it's two exchanges. Okay, and then likewise, if you want to write, if the master wants to write, then the master sends the address in the first exchange and the data in the second exchange, and the slave never sends anything back. Just or optionally, you could send back some sort of acknowledgement in the second byte, optionally. But if it does send an acknowledgement, it would only be able to acknowledge to the the address, the first byte. It wouldn't be able to acknowledge the data, so it would be kind of pointless to do an acknowledgement. Okay, so so I tried to show that here, what happens in each what's going on in each byte. Okay, so here's a timing diagram. Here's an example. I think this is probably a little easier to see. So this is a transaction. The transaction is defined by the slave select being low for 16 cycles. Now, you'll notice that the slave select is actually not marked as slave select here. It's called CS, which stands for chip select. And this is just an alternative name for slave select. So don't get too hung up on the names, because different vendors will sometimes call these signals a little different. And this timing diagram I actually got from a data sheet. So I forget which one. I think this was from the accelerometer that we were using, that we're hooking up to our board last spring. So they use a little bit different terminology, but it's not a big deal, because what's important is that you understand the purpose of these. So chip select, slave select, same thing. Then you've got SPC. That's your clock. Obviously, it's the clock. It looks like a clock. It's up, down, up, down, up, down, up, down. So the SPC is the clock, and I have no idea what SPC is supposed to actually mean. I mean, it's the clock, but I don't know what the letters what they're trying to say there. And then you've got SDI and SDO. I think SDI is serial data in and serial data out, which obviously correspond to MOSI and MISO, right? So like I said, I don't get too confused, because these vendors use different names for these. Okay, but obviously it's pretty clear from looking at here that the CS is the chip select. It's being held low. The SPC is the clock, because it looks like a typical square wave here. And then the SDI must be the MISO, because the MISO, whenever you do a transaction like this, you always start out with sending data from the master. So you see data coming out of the master first, and so that's the master, and then the slave responds. And because we've got master data first and slave data second, this is obviously a read. Now you'll notice that there's a couple things that are strange here, though. The SDO, which is the MISO, master in, slave out, is shown as a kind of instead of a gray shaded area, it's like a middle line, which is meant to designate a don't care. But I would expect them to also have done this for the MOSI during the time, during the second byte time, right? Because the master is not going to be sending anything here. It should be a don't care. I'm not sure why they showed it this way. Maybe in this particular chip you could send, there was some purpose for that second byte being sent out the MOSI during a read operation. I'm not sure, but this was actually a read operation, because this was how you read the acceleration data. So I'm not sure if you're doing a read, you send the address, you expect the data back the next time. Not sure what the master would be sending during the second byte, but it looks like it's sending something here. So I've color coded these two phases, these two transactions. I've kind of put them in these shaded boxes. And then for a write, notice that in the write, it's not even showing MISO, because the MISO is always a don't care. Because when you do a write, only the master is the only one that's talking. It sends the address and the data out, and the slave just needs to respond to that. But there's no acknowledgement. Now you might say, why are you emphasizing that? Well, I'm foreshadowing a little bit, because the next protocol we look at will have acknowledges, but there's no acknowledge for SPI. You just hope that it worked. Okay, so here's an example. This is from the exam last spring. In the following SPI transaction, assume the transaction address is stored in the least significant 5 bits, and the read-write flag is stored in the, oh yeah, so I should have pointed that out. Sorry, let me back up here a minute. So notice that in this timing diagram, the bits in the first byte being sent are labeled. AD0 up to AD5, and then you have MS with a bar above S and an RW with a bar above W. This is meant to signify what the bits mean. So the data bits, which actually are address bits, there are 6 address bits here. And then there's 2 more bits that are flags, one of which is a read-write designator, and the other one is a multiple or single designator. So the reason they put these bars here is because if this first bit is a 1, that means I'm reading, and if it's a 0, it means I'm writing. And so, in other words, so write is kind of complemented, right? And the read is not. So read is active high and write is active low. And likewise, with MS, multiple, you put a 1 in that bit slot, and that means you're doing multiple. And if you put a 0 in that bit slot, and when I say bit slot, I'm talking about the second bit from the, the second bit transmitted during the first exchange. If that bit is a 1, it's a multiple, and if it's a 0, it's a single. In this case, I can tell from the timing diagram, even though there's no value for that bit, I can tell that this is a single transaction because the slave select goes high after only 16 bits. And 16 bits is only enough time to do a single read, single transaction, or single operation, I should say, because you could have one transaction that encompasses, two bytes of reading or writing, which would be not 16 bits, but 24 bits. Okay, so if that makes sense, that there's different bits defined there. Now, keep in mind that, yes. Oh, sorry, M should be, sorry, I missed the first question. So the M should be complemented instead of the S. No, I might have said it wrong. The M is not complemented because in this protocol, the M, if that bit slot, if that flag is 1, then that's a multiple, and if it's a 0, it's a single. That's supposed to give semantic meaning to the value in that flag. I might have said that wrong when I was reading it. Sorry. But reading this the way it's written here, multiple is you specify multiple with 1 and single with 0, and the logic, yeah. So for the MS, yeah. So that's what I was saying. So the MS is a flag that's telling the slave whether it should expect 1 additional byte as part of this transaction or multiple, right? Essentially is what that means. So if the MS field is a 0, that means the total transaction is going to be 16 bits. If the MS field is a 1, then that means that it's going to be more than 16 bits. Yes, that's correct. So whenever there's 16 bits, it must have been a single. That's right. In fact, that's a good question. It kind of begs the question, why even have that bit? Because the slave is going to know if it's a multiple or single based on the slave select. If the slave select is asserted for 16 cycles, then it's obviously a single. And if it's asserted for more than 16 cycles, it's obviously a multiple. I guess that's just, I don't know, maybe to give the slave a heads up ahead of time. I don't know. I'm not sure. That's a good question. I never thought of that before. That never occurred to me, but it seems, you're right, it's redundant. Now, keep in mind, though, that those flags are defined only for this specific peripheral. Okay, so I mentioned that whenever you implement a transactional protocol on top of SPI, that is up to the individual vendor who's building it. So, oh man, I'm almost out of time. So these are not part of the SPI spec. These bits and their meanings you'd have to read out of the data sheet for whatever you're talking to over the SPI bus, essentially, right? So these were specific to the accelerometer, but it's pretty common to do it this way. Okay, so I got a few minutes left here, so hopefully I can make it through a couple examples. So in the following SPI transaction, assume the transaction address is stored in the least significant 5 bits. And the read-write flag is stored in the most significant bit of the first byte transmitted. So basically what all this amounts to is I'm coming up with my own protocol. I've made up a protocol. It doesn't necessarily match the one I just showed you. So the protocol defines, really it's mostly what information is in that initial byte that's sent across the channel from master to slave. So what's the transaction? Okay, well, looking at this, first of all, how many bits we got here? Well, I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 16 bits in this whole transaction. This transaction, of course, denoted by the slave select being low. It's low for 16 cycles, so it's a single transaction. I note that the MISO line is always 0. So that tells me that this is probably a write operation, sorry, because the MISO is, the slave isn't returning any data to the master. The slave is just kind of just, not done anything with MISO. That's not necessarily true though, because it may be a read and the response to the read might have been all zeros. So I'm not going to assume that this is a write based strictly on the fact that the MISO is flatlined. But it looks to me, usually if the MISO line is dead during a transaction, that usually means you're doing a write. The master's writing. But let's confirm that. So the read-write flag is stored in the most significant bit of the first byte transmitted. So pretty much I'm just looking at that first MOSI bit. And what is it? It's 1. Okay, so what does 1 mean? Okay, well, I guess 1 must mean write. I didn't specify that though. In the following, assume the read-write flag is stored in the most significant bit. Okay, well it is, and it's a 1. So, okay, so this question is a little vague. I should have said that if the read-write flag is 1, that means a write. So what I should have did is I put a little, in fact, maybe that's what happened. Maybe I lost the bar. So in this case, there should be a little bar above well, actually, I shouldn't say that because I guess it could be either way, really. But I'm going to assume for the purpose of this example that if the read bit is 1, that means I'm doing a write. So there should be a bar above the R here, meaning that if that first bit is a 1, which it is, then that means I'm doing a write transaction. And I say that because MISO is dead. It looks like a write, although this could have very well easily been a read. Not only that, though, not only is MISO dead, but notice that MOSI is also switching in the second exchange as well, which also is evidence that this is a write. Because if I was doing a read, then MOSI should have went dead during the second transaction because it would be expecting data back from the slave. So based on the fact that MOSI is dead throughout the whole thing, and the fact that the master is continuously sending data throughout the whole transaction, I'm thinking this is a write. This is a write. Okay, so what address am I writing to? Well, now I got to look at the 5 lower order bits from the first byte. So this is going to be bit 7, bit 6, bit 5, bit 4. Okay, so bit 4 down to 0 is my address. So my address is going to be 01000. So that's 8, address 8 in hex. So that was a little weird. I had to count out, obviously first 8 bits. The first bit I care about, the last 5 bits I care about. I don't care about the remaining 2 bits in between. And you might say, wait a second, if you don't care about them, then why is the master toggling during that period? Well, these are randomly generated. These came out of a program I wrote that randomly generates it. So it might seem weird that the master, like this bit and that bit, the second and the third bit, are don't cares, but yet the master is setting the first one of those to 1 and the second one to 0. It's like, why is it doing that? They don't cares. Well, they don't care, so just ignore them. So the address is sent, it's basically 8, right? And then the data I'm writing to address 8 is going to be in the least significant 8 bits of the whole transaction, or the 8 bits of the second exchange. So I'm going to count from so to do that, I got to go from the end and work my way to the left. So 1, 2, 3, 4, 5, 6, 7, 8. So the master is writing 1, 0, 1, 1, 0, 1, 0, 1. And you might say, why'd you start at the right? Well, because I can count 8 bits from the right. Okay, so I'm actually a little over time. I'm sorry about that. So that's an example. I'll go through more of these examples next time. I'm going to go ahead and just release the quiz the way it is. The quiz obviously will ask questions about SPI. I didn't get through all the topics, but remember that you've got a whole week to do the quiz. So this way you can open it and take a look at it. You don't have to do the quiz until after the next lecture on Monday. So by which time I'll have thoroughly, finished the SPI material. So don't panic if you feel a little overwhelmed by the quiz. You can always just wait till after the next lecture to answer it. So I think we should be in good shape. Any other questions before we stop? Yeah, I'm getting some pings. I think those are private messages, so I'm afraid to switch over because oh, I can do that because I'm not sharing my whole screen. Never mind. Duh. Uh-oh, Collaborate's not responding to clicks. Okay. Oh no. Okay, let me stop sharing. Uh-oh.
Would it help if I just read them to you?
Yeah, my whole screen, my whole Collaborate is locked, is hung for some reason. I'm not saying I can't click on. I'm not going to be able to stop the recording either. So hopefully I don't lose it. But go ahead and read them to me. Yeah, thank you, Charles.
So yeah, I see one. So if there were private messages, obviously you won't have those. So there's Adam asked, can you post the updated PowerPoint?
Yes.
And Adam also asked, so there's no time limit from when we open the quiz.
That's right. Oh, here we go. Looks like it released.
Okay, cool.
Oh, no, it didn't. It's still hung.
Oh,
what's going on with Collaborate? Okay. Yeah, but those are easy questions. Yeah, the quiz is unlimited time. Obviously, if you have the quiz open when it closes next Wednesday, it'll automatically submit, but you have unlimited time to actually take it. The exams won't be that way, though. The exams will be timed, but the quizzes aren't. Was there anything else?
I don't see any other chat messages. So let's see. Yeah. So
okay.
If anybody had any other questions, then you should post them now or send them in an email or something. Robert asked, will exams be similar to the quiz format?
Yes, they'll be similar. At least we're planning on that now. Last spring when we ran this course, we actually had some like short answer questions on Moodle that we manually graded, and we might do that for the exams. But I mean, the overall, they'll still be done through Moodle, and it'll either be multiple choice or short answer. I don't know how else to do those things on Moodle. So unless I come up with something better, that's how it'll be.
We did a couple of like matching questions last year, I think.
Oh, we might have. I don't remember that.
They're kind of weird though, like when you make them in the Moodle interface. So I think we only did like one, and we were like, oh yeah, this is like really annoying to set up. So.
Okay. Well, that's if that's all the questions, I think.
I think it looks like I have rights to. Oh, hold on, we had another one. How difficult are the questions on the quiz compared to the examples?
Oh, they're very similar. I took the examples directly from the previous, the last time I taught the course, so they'll be similar. They're also, it's also common to have, formatting errors and stuff, though. Unfortunately, with the way the Moodle works, well, I'm getting better at that. But if you see any bugs, let us know. No, there's no lab session. I saw that one. There's no lab sessions for the class, unfortunately. I guess things are going back to normal in the fall, which is good. So eventually, but that doesn't help you guys, unfortunately.
I think we are going to have some programming assignments, which will be kind of like a lab. I guess the question would be is like, how would you? Because like me and Philip would normally be running the labs if there were labs, and I'm not sure how you translate that into a online setting. So kind of the way that we intended to do that is just we kind of have office hours and they're by appointment because we'll just kind of work with your schedule and then we can just do kind of one-on-one. But if you know, I don't know if there would be, I don't know if it would be productive to have a, here's a like set time. And because like if you've got like 15 people there or something, I feel like it's going to be hard to get through everybody's questions, right? Because only one person can talk at a time in like an online format. But like, so yeah, I don't know. So I don't know that we're like super made up on that yet. But yeah, just I would say, so yeah, to answer your question, Robert, I would say just send us an email, include me and Philip, and we'll set up a time. I think, you know, normally if it's on a, if you email us on a business day, you know, we should be able to get you in, you know, within the next business day. You know, possibly faster, you know, unless you've got some really weird scheduling constraint or something. But in general, I think between the two of us, we have pretty good coverage of when we would be able to meet with you.
Yeah, last semester it worked out pretty well with, you know, meeting with the TAs over you know, teleconference.
I think it worked well, although I was disappointed not very many people took advantage of it. There were like 4 people that kind of did office hours kind of regularly, and then everybody else kind of didn't really hear from them. So you know, definitely utilize that, guys. Like it's we have that available because we want you to make use of it.
Okay, well, great. I think we got through all the questions. We'll go ahead and tie it up for today. Next lecture, I was planning on ending a little early to give you some time to look at the quiz. I'll probably end the next lecture a little early on Monday to give you time to look at the quiz, so or to work on the quiz for those of you that want to wait till Monday. So if you have any other questions, feel free to email us, and we'll talk to you on Monday. Thank you, guys.